Hello and welcome to this reality simulation webinar. My name is Evgeny Shapiro. I'm the product manager responsible for Realis Fluids products, which include 3D computational fluid dynamics, Vectis, 1D computational fluid dynamics, Wave, and our faster than real-time Wave RT products. Over the next 30 minutes, I'd like to give you an overview of some of the new and exciting features in our third release of 2022. In today's webinar, we focus on our 1D fluid products, Wave and Wave RT, which provide engine digital twin capability for design, optimization, virtual calibration, diagnostics, and increasingly maintenance of your engines. Our 1D fluids products, your predictive engine plant model, include a number of capabilities delivering fastest on the market real-time physics-based simulation. Support for complex fuels is enabled by a detailed kinetics-based toolchain with resolution of fuel composition effects from properties definition down to combustion modeling and emissions. Both the 1D Wave and real-time Wave RT deliver best-in-class acoustic predictions. These features are informed by our engineering expertise in our business, which is embedded in software workflows we deliver. Finally, 1D Fluids products are seamlessly integrated in the wider Realis ecosystem, including tools for system simulation, 3D computational fluid dynamics, and mechanical analysis. This 2022.3 release of Realis 1D Fluids focuses on helping our customers address the challenges engine developers are currently facing, namely the drive to develop even more refined, low-emissions green powertrains, while at the same time reducing the costs of the development process. In order to address these challenges, in this release we focus on features which increase predictive capability and also the workflows and user experience items which help save the most precious commodity of any digital analysis and digital engineering team, engineers' time, and which help distributed teams develop accurate engines models faster. In this release, we have introduced new predictive models in Wave and Wave RT for diesel combustion and emissions, as well as UHC emissions for SI applications in Wave RT. We have also added an extended set of flame speed models for a wide range of gasoline blends, and we further improve usability of process setup for complex models with the delivery of the signal interfaces overview, part of our Clean Canvas initiative, session comparison tool, and new acoustic post-processing features. Our support for import of GT power models has been significantly improved for diesel applications. And finally, we have added support for new national instruments, Veristand, hardware envelope system. Let us dive into some of these new features, user experience improvements, and workflow enablers, and consider what the simulation challenges are, what are the solutions we provide, and how our users can access these solutions. Let us start with the new diesel modeling functionality in both Wave and Wave RT. The challenge we're considering is the need for increased accuracy in modeling of future heavy-duty and off-road sustainable diesel powertrains. Now more than ever, we need refinement and optimization of these powertrains to lower emissions and improve performance. Wave provides an answer in the form of the new diesel predictive combustion model. The model is based on the diesel predictive functionality which we released in real time in 2022.2. It is accessed through a simple user interface with the same setup covering both Wave and Wave RT. The model supports multiple injection strategies, and the typical results are within percentage points of the test data for heavy-duty applications. Accurately modeling emissions in real time unlocks the potential for the optimization of heavy-duty diesel powertrains for lower carbon future. In this release, we have added a new diesel NOx model to our faster than real-time flagship product. The model is easy to set up and can be calibrated within minutes on high-performance computing clusters using advanced surrogate optimization, delivering results within 12% for NOx for full, part, and low load conditions. Let us have a look at an example of application of these models in WAVE and WAVE-RT to a heavy-duty engine from a leading European OEM. The engine in question is a 6-cylinder 6.7-liter heavy-duty engine, 104 mm bore, 132 mm stroke. The test dataset contains 97 operating points, featuring both single and two pilot injection strategies. The models applied to model physics predictively include KK turbulence model, which has been modified based on recent research at Oxford Brookes University, and diesel predictive WAVE and WAVE-RT combustion models. In order to introduce the modeling approach and, more importantly, model tuning approach, it is necessary to note that predictive modeling for engine applications is a complex matter, as the engine represents a strongly coupled system, where flow and thermal behavior, turbulence, and combustion are intimately interconnected. So in this case study, we are modeling and simultaneously tuning flow, thermal, turbulence, and combustion phenomena, and separately tuning emission submodel. The resulting model features multiple inputs, illustrated here through WAVE GUI input panels for convective heat transfer, turbulence and flow, and predictive combustion and NOx submodels. The modeling expertise of Realis team allows reduction of this complexity in terms of the multiple inputs to a reduced set of inputs which are sufficient to tune the model and sufficient to obtain excellent agreement with the test data. For the model tuning, we use the capabilities of Realis RDesk Tuner. It's a built-in optimization tool which uses advanced surrogate optimization to automatically simultaneously tune multiple parameters of the model to desired accuracy. The reduced set of model tuning parameters from all the parameters available for the flow, thermal, turbulence, and combustion is based on an extensive correlation study and is designed to capture all stages of diesel combustion, so diffusion, premixed burn, and diffusion burn. Convective heat transfer multipliers are added to the set, and we also add two calibration parameters for NOx model, rate multiplier and cumulative multiplier. The target parameters cover performance through indicated mean effective pressure and airflow, combustion through maximum pressure and the 10 and 50% burn points, and also engine out NOx. The selection of tuning and target parameters for a particular class of engines is something which forms a part of the optimal workflow which we deliver for our customers. The process of the simultaneous tuning of multiple parameters for 97 cases of the operating map uses high-performance computing cluster backend. The tuning takes 31 minutes on 200 cores, with the emission model calibrated separately, taking 13 minutes on 52 cores. The calibration process is extremely fast, which is helped by the real-time multiplier of the model in the range of 0.17 to 0.18, depending on the RPM, depending on the load, on a relatively moderate specification hardware. So let's have a look at the results of the model. The comparison between the test and simulation is quite good. We can see that the heat release rates are captured well for different pilot strategies for full load, part load cases, and low load cases as well. The IMP and airflow are predicted to within 10% and 3% of test data for 90% of mark points, and maximum pressure to within 4.4% of test data. We can also see that the probability distribution for the deviation of IMP and airflow shows that we are more likely to find cases within this 97 case set with even lower deviations from the test data. We can also see that combustion characteristics are captured very well, with 90% of map points for B10, 10% burn, and for B50, 50% burn within 2.2 degrees of test data and 1.7 degrees of test data. And also the probability is well conditioned for both combustion points. Looking at the performance of our new 2022.3 NOx model, we can see that 90% of map points are captured within 12% of the test data. And also the speed torque map of NOx compares very well between the experiment and the simulation. In order to demonstrate the performance of a new diesel predictive combustion model in WAVE, what we did is we took the settings obtained from our desk tuner for WAVE RT and applied these settings directly to WAVE donor model. And we can see that the results demonstrate also excellent agreement with the experiment for IMAP, maximum pressure, 10% and 50% combustion burn points for low load, part load, and full load. It's interesting to note that we can tune directly in our desk tuner WAVE model, so it's possible to export an FMU of WAVE and use the FMU tuning task in our task with the same surrogate optimization method. However, it's much faster to run the tuning on a faster than real-time model, WAVE RT, and the results are directly applicable to the donor model. Our next feature aims to address the challenge of accelerating acoustic analysis and help easy identification of resonances in the engine plant model network. Accurate representation of the pressure waves and flow phenomena in 1D are essential, and this is where WAVE excels. However, it's also necessary to be able to visualize this so that we can understand the behavior of our engines. In this release, our post-processing and visualization solution, RPost, has been enhanced to allow users to plot flow quantities and pressure, as well as perform frequency analysis in the wave flow network. The new network plot also benefits from all the data manipulation facilities which are available in RPost. Let's have a look at how it works for this model of 2-liter turbocharged gasoline engine. In this model, we have a number of complex components which can make acoustic visualization, flow visualization interesting. And I'll focus on the two mufflers, and specifically on the second muffler, which has been merged on canvas and is represented by the submodel here. In order to have the data available for visualization, we need to prescribe that this data should be stored during the simulation. In the WaveSolver solution in the Outputs tab, we can see the outputs, and here we can add values which will be available for the network plot. In this case, I have added basic pressure and temperature so that we can see the pressure waves as they enter the muffler. Once WAVE solution has been completed and the data is available, we can open the data in RPost. And for this model, we can create a new network plot by clicking on this button. So the network display provides a counter plot, a color plot of values for which the data is available in the model on the canvas. We can browse the cases as with any WAVE visualization. Here we have two cases simulated for this model, and we have a number of data sets available. The summary data, which we requested, pressure and temperature, Also, the data which wave outputs by default when we are switching appropriate settings in the output panel, such as densities on the left and right side, heat transfer properties, mass flows, etc. for ducts and Y junctions. We also have ability to conduct frequency analysis. So frequency analysis is conducted on pressure, and we can visualize the frequency either in linear mode or by looking at decibels. Now let's have a look at what's happening near the muffler as an example. So I'll collapse the plot to give me a slightly better view. And then switch to frequency. Let's say, for example, for the second case in the simulation, switch frequency to decibels and look at the second order. And adjust the scale slightly so that the wave is more visible. Okay, that's better. So we can see the higher RMS of pulsations near the entrance to the muffler. On our post canvas, we can dive into the component representing the muffler, and then it's also visible how the wave which enters the muffler is dissipated. So in this case, there are no interesting resonance happening in the muffler, as the muffler has been well designed and it's doing its job well. This new functionality in our post is covered in detail in our documentation, and also our existing acoustic tutorials in Wave have been enhanced to illustrate the post-processing using our post. Visualization in 2D on a wave-flow network provides a great method for the analysis of pressure distribution and pressure pulsations. However, for complex geometries, a better insight can be obtained by directly examining distribution of flow quantities, pressures, and pressure frequencies in 3D. In this release, we introduce a new feature to address this challenge and enable precise analysis of pressures and temperatures in complex exhaust, intake, and muffler components. The feature is available through a new 3D visualization task in Wave GUI. Users can have access to time data, cycle averages, and frequencies, and export these into 3D, simplifying both analysis of component performance and, what is actually equally important, communication of results to end customers or a design team. Let's have a look at how this feature works using our 2-liter turbocharged gasoline engine example. The engine we are using for this demonstration is the same engine as the one we used to illustrate network plots for Wave in our post. However, a slightly different modification. So in this modification, the second complex muffler has not been merged. It hasn't been decomposed into 1D elements, but instead it's represented by a complex component. In order to visualize the solution of this complex component, I'll add a new 3D visualization task to the model. And this task allows me to configure what I'm exporting, how I'm exporting it, and what is the 3D geometry I'd like to cross-plot the results with. So the data source, we can, by default, we're picking up the last wave solver run, but we can select a specified WVD results file. The geometry, I'll select the geometry of the second muffler here. This geometry is in Ricardo standard tri format, and this type of geometry is exported from other tools in Wave toolchain, namely from Wave Build 3D. The output then defines the name of the point cloud file where the results are stored. The solution is visualized in point cloud file where points correspond to the locations of the data. in the wave model. And finally, what would we like to process? So we'd like to process the second muffler component, and we want to see frequencies. When we run the 3D visualization task, save the session, the task extracts the data, translates it into a viewer format, and creates an RBF file, the batch file, which we can open in our viewer and which actually generates the visualization. Let's open our generated batch file in our viewer. So in our viewer window, we can see on the canvas the 3D component, the point cloud file with the data generated by Wave 1D solver, and also the labels which identify these points by the names available in Wave. So let's have a look at the wave in the second order, which enters the muffler and dissipates in the muffler. In order to do this, first I'll hide the labels, and I will also slightly increase the transparency. Then in the point cloud, you can see the data sets which are available to us. So we're looking at pressure amplitude for the second case, and for the second order at 200 Hertz. It's highlighted slightly so that it's clearer, and we can see this high amplitude entering the muffler and then low amplitude elsewhere in the muffler. Now, point cloud visualization in our viewer is a very powerful method of visualization. So we can examine the data, or we can adjust the data and grade the points according to the data values, and we can also probe individual data points to find out where in the wave model the data point is, and also what the exact values of pressure amplitudes in this case are. A full description of this process and its usage is available in Wave Help and in Wave Manual, and also 2022.3 installation includes a new tutorial demonstrating how 3D visualization can be applied. Our next new feature aims to help our users accelerate engine plant models development and also reduce the possibility of user errors. Complex engine models can feature hundreds of sensors, actuators, and control signals. In previous releases, we have introduced new clean canvas methods, which allow users to easily connect these to their engine model. Mistakes in connectivity or units can cost valuable engineers' time, and in this release we introduce a new signal interfaces overview, which allows users to easily examine important properties and connectivity of actuators, sensors, and send and receive signals in a single compact table view, and also navigate to the related elements in the model. This functionality makes it much easier to inspect and troubleshoot complex models, and it saves the most valuable resource of any CA team, which is time. To illustrate the signal interfaces overview, let's have a look at our 1.4 liter turbocharged direct injection engine example from our tutorial database. When we open the model, the signal interface overview panel appears, and it allows you to see actuators, sensors, send and receive elements present in the model. It also provides a handy field which can restrict the view to elements with a specified name. The table itself provides access to properties which are most interesting to inspect. For example, for actuators, we can see the name, the type, input, unit, bandwidth, connected elements, sublocation, and also whether or not this actuator is supported in real-time WaveRT tool. It also provides access to navigation. So, for example, by clicking on actuator here, we get the edit panel of this actuator, and the actuator is highlighted on the canvas. In the edit panel of the actuator, there is also a list of actuated elements, which shows that throttle is actuated, and we can get the throttle properties by clicking the pencil button in the edit panel. Similar navigation is available for all the other elements, sensors, sends, and receives. This simple functionality provides us with a very convenient way to have an overview of all the connectivity of actuators, sensors, sends, and receives in a single place, covering the complete model. And it helps us inspect this connectivity and avoid mistakes in the connectivity, which ultimately saves us time down the line. The access to this functionality is enabled by default. So all the new models or existing models will have the signal interfaces overview table when you open them. It's described in detail in our manual, and also because it's there by default for all the existing models, it's also illustrated through the existing Wave tutorials and examples. The last productivity feature of this release is designed to save time and help simplify collaboration between team members. It is the comparison tool, which is introduced in Wave plugin in 2022.3. This tool allows engineers to compare sessions and identify the modifications made in an easy-to-read tabular format, either directly in the GUI or in Excel. Apart from providing a handy comparison between different model builds, this tool can also be used to troubleshoot models by comparison with the correct reference model. Examples of issues in the model, which can be easily identified by such a comparison, include mistakes in the input fields and units, incorrect connections, etc. Let's see how this tool can be applied to compare models and identify mistakes or modifications using our 1.4-liter turbocharged engine example. Let's go back to our test model and make some modifications representing common mistakes or legitimate changes in the model, and then compare against the model reference to illustrate how this comparison works. So in this model, I'll introduce a mistake in units, which is a common user mistake during model building. So I'll take the ambient pressure actuator and change it to actuate kilopascals. Also, I'll change the unit of the sensor to pascals, change the bandwidth, and actually connect it to the wrong cylinder as well. Then we'll make a legitimate modification which another team member did when tuning, for example, post-flame oxidation model. Let's say modify the constant and introduce another change which is more representative of a mistake when copy-pasting data from Excel. So, for example, we will take exhaust manifold temperature from a different place, and it's slightly different than the original model. So we'll save this model under a different name, for example, modified, and then use the comparison tool, which is available through this button on the toolbar, and compare with the previous session. The results of the comparison will be summarized in the output window. So here we can see that our current model, B017 mode, has been compared against the reference B017, and the table below provides the list of changes which were done between these two models. For example, we can see our change in units of the sensor for cylinder 1 and for actuator for ambient pressure. We can also see our changes to the temperatures of the exhaust manifold. It is very convenient to view these differences directly in the output window. However, for models where the number of differences is very substantial, the format of the output window may be not amenable to displaying very long lists of differences. So in order to help our users analyze differences between such models, the comparison tool also outputs a CSV file which can be read in Excel. So we can see here that the results of the comparison were written to a file, and the CSV file appears with the name of the first model, _compare, name of the second model. The comparison file appears in the session directory. We can open it in Excel. And once it's in Excel, we can easily filter and sort by the reasons of differences and examine cases where the number of differences is substantial. The resulting functionality makes it easy for our users to examine differences between different builds of the model and also catch mistakes in the model and compare their model with the models modified by their colleagues. Apart from the headlines, this release is packed with other enhancements for Wave and Wave RT. We have a new sensor to report valve event angles at user-defined lift height, which provides users with complete flexibility with respect to using valve opening-closing reporting with their workflows. We now export time-based injector types to Wave RT, and we support PID controller in Wave RT as a direct export from donor model. We have added the ability for tuner to store time data for the last cycle. This is a new output which simplifies substantially comparison of test data for pressure and heat release traces. In 2022.3, our desk tuner should be tolerant to model divergence for Wave RT. Sometimes, too generous tuned value limits specified by the user can drive the engine into an area where convergence spray is problematic. For example, combustion is too fast to be resolved with specified Wave RT timestamp. This new feature makes tuner ignore such points, ensuring that we can get correct results from the tuning, even with the mistakes in the setup. The release also features new heat release analysis process, which improves substantially our previous process. It simplifies and streamlines the setup of prescribed combustion modeling based on test pressure traces, in particular when the number of cases in the model is substantial. Finally, the release features 15 updated or new tutorials and examples. These illustrate new features, and also a part of the material has been converted to the Autodesk workflow. This one is particularly important as Realis team intends to obsolete wave build process in the upcoming releases, and we would like to make customer migration to our Autodesk process as easy as possible. This release builds on the strengths of Wave and Wave RT delivered in the previous releases, and we'd like to draw your attention to some of these, including for Wave, enhanced complex network visibility controls, making it easy to deal with models featuring hundreds of sensors and actuators, automated tuning of Wave FMUs, including using automated tuning on high-performance computing backend, and the new workflow for heat balance analysis. And for Wave RT, automated tuning of Wave RT models on high-performance computing clusters, and full two-stroke engine support. I'm happy to answer any questions you might have about this exciting 2022.3 release of Wave and Wave RT. And if you're watching this in a recording, you can find out more at www.realis-simulation.com or contact us at support@realis-simulation.com.